Hello, everyone. Thanks for joining in. I'm Abhishek. I lead the MLX team within Cortex. Cortex, for those of you who might be unfamiliar, is Twitter's central ML group. Today, I'll be talking about our work on embeddings and how we think of the role of embeddings in today's machine learning pipelines. Diving straight into the agenda for today, I'd like to begin with a quick introduction to our team and its charter, which I think will help motivate me the work we are doing. Following that, I'd like to briefly introduce the concept of embeddings. Assuming most of the folks here are fairly familiar with the concept, I'll try and keep it short. Then I'll discuss the use cases for which someone might want to use embeddings. In that, I'll also cover how various teams within Twitter are doing so. In the third part of the talk, I'll focus on the details of the embedding pipeline that we have built. The aim is to position embeddings as first-class citizens of Twitter's ML infrastructure. And I'll go into the details of what that exactly means from our perspective. I'll end with an insight into our ongoing and future work to further build on the initial pipeline work that we have done. So with that, let me just quickly introduce the team and its work to you. As I said, I'm part of Cortex, Twitter's central machine learning team. It constitutes of both the ML infrastructure teams as well as the product modeling teams. The specific team that I'm part of, MLX, or the ML extended environment, the charter is to unify and advance recommendation systems at Twitter. When we talk of recommendation systems, it usually refers to personalized suggestions of what? Literally anything when it comes to the Twitter context. And we have a lot of systems in a lot of areas where we provide these personalized suggestions. Some quick examples. On your home timeline, you see these tweets. These are all ranked according to what we think is the user's taste. There are the hashtags that are, again, personalized to the users. The other users that you might like to follow are also, again, based on your tastes. Similar things you can see. You probably see emails coming from Twitter recommending some tweets that you might have missed out or the people that you might like to follow. There are other notifications, et cetera, as well. And in a sense, Twitter could be thought of as one big recommendation system if you think of all the products that we have and how they function. All these recommendation systems are thus trying to rank some form of content. It could be a tweet, hashtag, depending on the product, for a user using ML models and utilizing the data about the user, the content, and their interactions. So what is MLX, my team, trying to do differently, and how does our work on embeddings come into play? That's exactly what I'm here to talk about today. And so with that, let me briefly again introduce what an embedding is and how we see that. Simply put, an embedding is a representation of a discrete entity in a continuous space. Most often, a machine learning model is used to generate this representation. The entity itself could be anything of interest, such as user, tweet, author, a word, hashtag, location, anything. We could learn a model to represent these discrete interests in a vectorized form based on some input data set containing the entity. It might contain a label or not, and you would choose a supervised or an unsupervised mechanism to do that. The interesting thing to note is similarity between embeddings in the resulting vector space is used to encode relationships. And I'll get into how we kind of exploit that. Note that the similarity in the vector space can take on a different meaning depending on, one, the domain, and two, the problem definition of the embedding learning model. For example, if you're embedding words, then we want to ensure the embedding contains some sense of semantic meaning. In case of users, for example, we might want it to encode information about their interests. Okay, why embeddings, and what exactly are we doing with it? And how is it different than what people are used to hearing about embeddings and their usage? So these are broadly the four categories in which we try to use embeddings and use them in our ML pipelines. I'll go over each of these in detail later. A brief value proposition for each of them. When used as model features, embeddings encode complex information about the represented entity and thus hold promise of improving prediction performance of the model itself when used as the input feature. Second, feature compression. This is something unique to what we have done. We have some papers out for this as well. When used for feature compression, embeddings can lead to dramatic improvements in overall efficiency of the ML pipeline and reduction in the infrastructure cost. Nearest neighbor search Again, neighborhood lookups on embedding spaces exploits the information encoded informed distance between embeddings. So this is of immense use in various applications. I'll describe what we do with that. Transfer learning. When used in transfer learning setup, embedding learning models can help with knowledge transfer between related domains. And this is of immense use when we work on multiple products that can be related any somehow. This brings in efficiency benefits in terms of training time and model quality. I'll now dive more into each of those separately. Model features. ML practitioners typically use one-hot encoding to represent categorical inputs or discrete entities like users. Most often that's limiting. Why? The one-hot encoded vectors are orthogonal to each other and thus are incapable of encoding anything about the relationship of the input entities. For example, how is one user related to another user, or how is the word queen related to the word king? This approach doesn't work well when the cardinality of the input space is very large, as it introduces huge amount of sparsity in the feature space. So all words in a language are all distinct users within Twitter. If I were to just one-hot encode them, the model wouldn't learn much. On the other hand, embeddings are output of machine learning models. What it means is now embedding, based on, again, how you learned your model, embeddings can conserve relationships among entities, which can then be exploited by a machine learning model when used as input features. Embeddings also compress the sparse input space into dense vectors, thereby getting rid of any sparsity issues. I think this is one of the more known use cases of embeddings out there. I'll again demonstrate it with a quick example. If these are the 4 users I wanted to input in my model for learning something, and if I were to one-hot encode them, these would be 4 users, and they would have 4 vectors, each of dimension 4. These vectors would not be able to capture any relationship between any of these 4 users, and they'll be very sparse. On the other hand, if I were to learn embeddings for each user by factorizing the follow graph on Twitter, we can start learning these relationships, and very likely do it with a dense and relatively smaller dimensional vector. The fact that, and we have these learned embeddings for users based on their follow graphs, something that we observe is like, this is just a made-up example, but the distance between Steph Curry and King James, if it's less than the distance between King James and Bruno Mars, it certainly is encoding some information, which I would have not been able to do otherwise. And it directly results into better model performances. A model using embedding as input feature thus will exploit the encoded knowledge. On top of that, assuming compactness of the embeddings, the model itself will require fewer parameters, resulting in faster iteration speeds and cost savings because you are now able to learn your models faster. Feature compression. Now, this is something unique to what one of our use cases. Why do we need feature compression, first of all, and how do we use embeddings for that? To understand why we need feature compression, let's assume a typical ML model that's serving traffic at Twitter scale. There are typically 2 groups of features there, offline and online. That's our terminology for that. Offline features, they remain fixed for a certain time window and are refreshed every so often. They're typically stored in a key value store and fetched from that at inference time. A typical example of an offline feature could be a user's feature like the user's age. Then there are other set of features, the online or real-time features. These are updated in real time and are thus constantly changing and evolving. So at inference time, every time you fetch a value, even if it's a few seconds apart, the value will change, and hence the output of the ML model will change. A typical example could be number of likes on a tweet. It's always evolving. So you cannot rely on a past snapshot of that feature. Now, adding more features, although good for models almost always, is prohibitive after a point at the scale we operate. The reasons are, more features means increased storage cost and network cost, because now you're fetching them from a remote store. It also puts a limitation on model complexity, because at the end of the day, all the steps that need to be carried out at the time of inference have a capped SLA. So if you're giving more at the time of fetching the features, you are limited in how much complex your models can be. On the flip side, this would mean that less features or compressed features mean reduced infrastructure cost and reduced latencies. But then The challenge is to being able to reduce this dimensionality without compromising on the model quality. So how do we do that? Thus, in order to achieve compressed feature space, we just leverage the fact that every layer of a neural network is actually learning a representation of the input space. So how can we exploit that? For every feature group identifiable by an ID, run inference on part of the network offline and persist the resulting embedding layer in a key value store instead of the raw features. Now, update the embeddings at the same update frequency as the raw data set. With this technique, we have achieved reductions in input space size ranging anywhere between 5x to 40x, depending on the input feature group and its relevance toward the label that the model is predicting. This was achieved without hurting the final model performance is the crucial part. Now we have the ability to scale and add more features without worrying about our SLAs or the impact on the model performance. And on top of that, it gives us core metric wins, meaning the end user experience is better. Either you are able to use that extra time for ranking more items, or actually, I'll cut that and first basically cover this slide because that might be some lost context there. So at inference time, when you have those embeddings stored in a batch store, at inference time, retrieve the embedding instead of the raw offline feature from the key value store and the online or real-time feature. So you don't do anything with the online feature is the thing to note here, because you can't really just take that computation offline. This has led to reduced cost of storage, network, and compute. Compute, interestingly, because part of the network is now computed offline. So you don't need as much complexity in the model that's been running at inference time. Reduction in latency has resulted in direct core metric wins by utilizing the extra time to rank even more candidates. That's what I said before. This is specifically something that might not be immediately come across as an obvious use of embeddings, but given the scale that we operate and the bottlenecks that we face, this has come out to be one of the very promising areas of further investment for us. Nearest neighbor search. Okay, what is nearest neighbor search? Promise it has nothing to do with searching for your neighbor next door. What is it then? Embedding entities in a space where you can reason about how similar they are to each other unlocks vast amount of possibilities. Essential component of candidate generation pipelines. What is candidate generation? It is a stage before ranking in recommendation systems where the application needs to narrow down the search space from a possible billions to a few hundreds that then can be ranked. Then how can we utilize embeddings in candidate generation? Well, we can co-embed users and the content in the same space. What that gives us is, then given a user, you look up its neighbors in the embedding space, and that can lead us to the content that the user is most interested in. Now, the interesting part is the power of this approach lies in the fact that it is possible to do nearest neighbor lookups without exhaustively scoring the whole space. This is made possible because of a class of algorithms called approximate nearest neighbors, or ANN, which we are heavily investing in. And it finds application in various other areas as well, apart from just candidate generation, which is query expansion. Given a string, can you give me others? And various other things. Similar media lookup, given an image, can you show me other similar media or news articles? And the applications are immense. Last but not the least, instead of just using the embeddings as input features, transfer learning exposes the ability to adapt the embedding learning function to the new model. So you're not just using them as model features now. Model train for one task is used in another. There are various examples out there in the literature for this. Typically, this happens by initializing network weights and then fine-tuning to the next model. It's very attractive from a business point of view. It reduces your development time because you have already spent some compute which you don't have to again. And enables cross-domain information sharing, which is really important in a company where we have so many of these relevant systems out there. And typically, they are not sharing as much knowledge across. So if our infrastructure enables this with ease, then we just unlock all of this. With that, I'll go into the details of what exactly we have built, what is the embedding pipeline that we have built, and what it unlocks. But before I dive into that, I wanted to briefly mention the goals that we have set for ourselves with the embedding pipeline. The overall motivation being that embedding should no longer be an afterthought for product ML teams. They should become a first-class citizen of the machine learning infrastructure within any company. So with that, the first one, quality and relevance. We want to enable adapting to evolving data distributions over time. This means that even if you learned embedding on a particular day, that it doesn't mean it stays relevant 1 month later as well. I'll show a quick example of some things that we found on that, which means that the embedding pipeline should be able to adapt to underlying distribution changes. Example, user behavior would change, usage of words would change, especially on Twitter, the vocabulary and its usage just changes. The new words are coming to the platform every other day. So we have to be able to adapt to that. If applicable, the learned embeddings should be of value across ML product teams. What typically happens is if one product team is working on their model, they do that in their own silos. They extract some features, they just work with that. The other team never gets to know about it. So how can we unlock that as well? The second is creation and consumption with ease. This should enable teams to learn embeddings at scale using the appropriate algorithm for their use case. I'll go into detail how we do that and how the pipeline actually enables that. This should also enable teams to consume embeddings at scale. They should be able to access embeddings both offline and online. And this is almost always underappreciated, how much work it takes to take a new data set into production and then being able to update it every time alongside your model, because there are immense number of versioning issues and infrastructure issues that come up with that. So how do we take that pain away from any product team, and how do we make that easy for them? The last one, sharing and discoverability. As I mentioned, there should be something that if there is a data set that exists in one part of the organization and they have found a way to utilize that, this should be easily made available to all teams across the organization. And how do we enable that through this? I'll again go into those details. So this is this is kind of the high-level stages of what we have built. These are the first stages are the item selection and data preprocessing. Then model fitting and benchmarking. This happens usually in a loop. You have the option to choose a particular algorithm while you're learning your embeddings, and also some corresponding benchmarks. Last, you have an automated way of, once you have an embedding that you're fine with, it automatically gets registered to the feature store that we have at Twitter, which unlocks a lot of things. And then I'll start talking about each of these in more detail. The important thing to note, though, is all these stages are orchestrated through the ML workflow that we have. This is built on top of the Apache Airflow framework, if people are familiar with that. It's an essential component of the pipeline, and I really want to emphasize that part. It lets us run the pipeline at a particular schedule with all the fail-safes built in so that we don't have to worry about it. It's not just us. Even if we were to worry about it, that's fine, but the comfort that it gives to product teams that they can just plug in a few things and everything else will be taken care for them, and they have a better machine learning model at the end of the day. That really breaks the barriers for them to start working with embeddings. It also lets us run hyper-optimization loops as part of the orchestration engine. So usually learning a machine learning model is, you always have these hyper-op parameters that you want to do a lot with. Again, the product teams don't have to worry about that. It automatically happens once they choose their data sets, once they choose their machine learning model. And all these stages are exposed as what we call the machine learning workflow operators. It provides the ability to the product teams to just learn and evaluate and expose embeddings with minimal overhead for them. They are not overthinking as to what it takes for them to learn an embedding or use it in their model in various different ways. A quick example to emphasize the point. The word-to-vec embeddings were trained on tweets written during different time periods shows significantly different relationships between words. So at the top, you can see President and Trump and President and Obama. These are word-to-vec models trained every 6 months. And you can see the similarities between the words changing. This is a much longer-term effect, but on Twitter, this doesn't only evolve over 6 months. There are new vocabularies, new words coming in every few days. We have to be able to adapt to that. There are more examples down below. Google and Pitchai, Cortex and Twitter, how with time, just the vocabulary can give us the sense of these relationships. And these are immensely powerful when fed into the machine learning models. Same applies for user behavior, hashtags evolving on the platform, et cetera, et cetera. Okay, so the first stage of the pipeline, it's item selection and data preprocessing. In the item selection phase, the product team would just come in and choose what is that entity that they want to learn embeddings for. Is it a word? And if it is a word, what are the kind of filters they want to put on it? They can just configure all these things. For user embeddings, they can just sample a particular user set based on their area of interest, and that's it. On the second stage, they would assemble the data set that represents the relationship between those entities. So if it's words, how do they want to model them? They get to decide that. And correspondingly, collect the data set according to the algorithm that then needs to be trained for model fitting. So for example, in our skipgram word embedding pipeline, we use this step to form a set of word pairs where word 1 appeared near word 2 in a recent tweet. In our user graph embedding pipeline, we use this step to construct a data set of user pairs where user 1 and user 2 are connected through a Twitter follow graph or an engagement graph. Second part, the model fitting. Once you have collected your data and you have massaged it in a way that easily fits into your the algorithm that you want to use for learning the embedding, then user can simply plug in pre-built algorithms. We have a host of them, and we are even researching and working on more that can work with different sort of underlying data representations or distributions and expose these data assets. They also have the option to plug in a custom algorithm if they feel so, and they have a very niche use case which we are not able to serve at the time. Again, as an example, in a skipgram word embedding pipeline, we use a gradient descent algorithm with negative sampling and assign embeddings to words from their skipgram pairs. In follow graph SVD pipeline, we use SVD algorithm to convert the adjacency metrics that represents the Twitter's follow graph. There are more. We are working on graph convolutions and other things that, again, people have the ability to not think about that, not invest in that, but still reap the benefits. Benchmarking, unlike with the classification or regression model, it's notoriously difficult to measure the quality of an embedding. Why is that? When you want the embeddings to be relevant across models and products, you're just not benchmarking one particular task that you will do inference on at the end of the day. The end use might also vary across teams. Someone might want to use it as a model feature. Some other team might want to use it for nearest neighbor lookups. Right? So how do we actually go about doing that? And also make it easy for the product teams so that they are not having to spend effort to just understand how good that embedding is and how is it kind of related to my task. Should I use it or not? Especially when new versions are generated automatically with an ML workflow, how do you expose the performance of these new versions, and how do the product teams get confidence in that as they use it? So we developed a variety of standard benchmarking tasks for each type of embedding. I'll go over some of those to just give a sense of what we are trying to do. The motivation behind all of these is that the benchmarking tasks are trying to evaluate a meta trait of the embedded entity by relying on the learned embedding as the only input about the entity. So as an example, user topic prediction. In this, we are sampling the users based on some and segmenting them based on their activity grades. Then this benchmark is evaluating the predictive performance of a regression model learned on the user's embedding itself only. And these topics are the ground truth because they have been collected as users join Twitter, they get to choose what topics they're interested in. So this is ground truth. There are some biases built in because they choose those topics, then as a factor of that, they're curating a follow graph for themselves as well. So if you think of learning and embedding on follow graph, then testing it on something that kind of affected the follow graph has biases built in. But there's only so much that you can get away from while we try to do this. Use of metadata prediction. So again, learning a regression on and evaluating the predictive performance of the model learned on the user embedding to predict a user's metadata. For example, can I predict the age or the geo of a user just using the embedding? Again, a very meta kind of task. Another one, user follow Jacquard. It basically is the Jacquard index of the user's embedding similarity and their actual follow sets. So if I were to embed all users and do a nearest neighbor search on them, and also as a ground truth, bring in their follow users that they actually follow, what is the Jacquard index of the two? Similarly, we have benchmarks of word embeddings and other entities that exist in the Twitter ecosystem. Also, again, users have the ability to add custom benchmarks and directly evaluate against their final training objective. Finally, once you have gone through this whole process of finally establishing the trust that you want to go with a particular version, then you have the ability to just directly register to what we call the feature store. It does a lot of functions for us. Once you register to it, you are easily able to join them in your batch datasets, take care of versioning offline and online, meaning when you're deploying a service or a new model, you are just with a click of a button deploying this new embedding that you have learned to a key value store. Versioning is taken care of. And a very intriguing challenge that comes in is when you are upgrading your model version, meaning you have just retrained it another day, or you have added another feature to it, and also you have learned a new version of the embedding, while the rolling updates are happening to the fleet, how do you take care of the versioning? You cannot have a version mismatch in the model and the underlying embedding. So all this is just captured by feature store. Product teams don't have to think about this. It also enables discovery, which is again a big part. If a particular team in its corner of the world is learning and embedding, they have as soon as they publish it to the feature store, along with all the benchmarks that they have obtained on that, get exposed through a UX. People have the power to come in and say, this is the very first model that I'm building. I want users' data. Okay, there are these embeddings that are depictive of a particular trait of a user. These are the benchmarks. Just pull that in. You don't have to spend time to massage the data, then be able to do that. So it helps teams get off the ground pretty easily. Given that, what's next? What are the things that we are actually working on next to the pipeline? New embedding learning algorithms. We still have a limited number of them. There's a bunch of research going on in how to extract value from big graphs. And we can almost every data set that we have can be composed in terms of a graph, how people engagement graph, some abuse graph. And you can just then learn things from them. Increasing number of data sets available as embeddings. So in order to get this flywheel going, we really need more and more teams start utilizing this, start publishing them to a central repo where it's consumed by more teams easily. Another big area of investment for us is large-scale approximate nearest neighbor solutions. The requirements that we have for ourselves doesn't allow us to just pick in any open source solutions that are available. We want to be able to do real-time updates to the embedding index. We want to encode filters as we are doing the query to the ANN index. Um, Also, a lot of the products in the company do online training, which means that you are actually updating, swapping your index just way too often at maybe at every 30 minutes. How do you do that? So we are investing huge effort into the ANN indexes. And it's of use across our product teams, as I explained before. Further exploration with embeddings as a means of feature compression. Uh, what I explained about feature compression, we tested it with one of the biggest ML teams at Twitter, and it has paid huge dividends. We want to be able to abstract it out in a way that every product team is able to use that now, and it's not limited to a particular team. And that's it. Thanks for listening. And just leave that there in case people are looking. Yes, please.
So one thing I want to know is basically when you're doing embeddings, what do you do on an offline evaluation? I think you talked about some benchmarking.
Mm-hmm.
Then if you're trying to recommend something,
Mm-hmm.
how do you build out data sets and how do you evaluate embeddings on those build out data sets, particularly to evaluate how embeddings are doing?
If I got your question right, you're asking within the when I'm learning a particular benchmark, what is the holdout data set?
So my basic question is how do you evaluate the embeddings that you got?
Uh-huh.
And then secondly, if you're doing it for a recommendation task,
Mm-hmm.
what is the process to create a build out data set that is not biased?
Yeah. So for the benchmark itself, in order to just only evaluate the embedding, you are basing your benchmarks on some ground truths that you know of. Again, follow graph is one, my age is one. The challenge, as I mentioned, is they're almost always going to be biased in some fashion or another. Now, what you can imagine is I'm learning an embedding based on your follow graph, but I'm trying to predict your age. They are going to be biased, but only if the embedding is capturing something about you would it be able to tell your age just from your follow graph, right? And there are like multiple of these combinations. So we are trying to operate when doing the benchmarks solely for embeddings, operate at a very metal level that irrespective of the data you're using for learning your embeddings, you're able to predict some of these things. And we see consistent variations as to, let's say, if I reduce the dimension of the embedding learned from the very same data set on the very same algorithm, there's a good correlation on how well I'm able to predict your age. This is just, I'm taking an example. So it means that operating at this meta level of ground truth data sets has some utility. On the second part, when a team actually uses this embedding into their model, they go about carrying on the same process as they do for their model, as in they have a time window where they are not training on, and they have to make sure that the embedding that was learned was not utilizing any data from the time window from which their holdout set belongs to. You have to kind of be double. You're not only concerned about your recommendation model, but also the data set that went into learning that embedding. You have to enable that. And so versioning, as I talked about versioning, that enables that through a long way. Because when you're joining with feature stores, embeddings already registered on feature store, what is happening is you are saying that my recommendation data set is from this day to the X to Y day. Now give me an embedding that I can use. It already knows that how to kind of get you away from these biases. This will throw warnings and errors if you're trying to kind of look ahead and cheat a little bit. Yeah.
So Abhishek, you mentioned that some abstraction of these embeddings are used across the team within Twitter. Is there a plan to have some level of abstraction of these embeddings to be used by other people outside of Twitter?
So actually, good question. There's been a lot of interest on that. And we are actually just trying to figure out what is the legalities around that, which is always the tough part. A lot of companies have reached out, and if there is interest, feel free to reach out, and we can just figure it out as we are doing with other ones. Yes, please.
How you decide upon the number of dimensions of the embedding? Because you're modeling and
My modeling, sorry?
Your modeling step and your embedding definition is different. It's not combined model. So how do you decide how many number of dimensions you use?
Not really, right? Well, it can depend on the algorithm. Depending on the algorithm, this can change, but this is again one of those hyperparameters mostly, and usually what we do when we register a particular embedding to the feature store, it's never registered with a single dimensional. So we would register, let's say, 50 dimension, 100 dimension, and like also a 300 based on again what the benchmarks were telling us and what an end recommendation model was telling us. And then the final product team is free to choose from them, and they have various considerations. If they're going for a higher dimensional embedding, they have to incur the cost of storing them, fetching them, etc. And they have to make that call as to how much improvement is it leading towards in their end model and how much they have to kind of sacrifice in terms of infrastructure. So there's never a right answer. People have to, again, experiment. Usually people would experiment with all three dimensions and make that call based on what they see. Yeah. Yes, please.
Do you have any strategies for interpretability of the embedding?
Yeah. So uh, first of all, before coming to the strategies, even the necessity of interpretability kind of varies from one case to another. People who are actually using it as just as model features don't really care as much. There are analysts who want to kind of look at it, they really care about that. We haven't put in a lot of time and energy as yet because till now, we haven't been interacting as much with the analyst side of the world. Although this becomes important as matters of fairness in ML and all these things come up, and there are like very active ongoing work streams within Twitter on how to evaluate our ML models, and then embeddings even more crucially, given all those concerns exist. So we have all those plans, and hopefully we'll be able to expose a priori those things as part of the central repository too. Yes, please, on this side.
So I assume you have some sort of a version control for the embedding.
Mm-hmm.
You have like embedding every few months, right? So for your downstream product teams,
Mm-hmm.
you found they use a multiple or a time series of embedding as a feature, and do they always keep up with the newest ones that you push out a new embedding, they immediately train a new model? Or
Yeah, this is sort of a pain in a sense because let's say there are 5 product teams. One is hyperactive about updating, the other one is not. Then how do you deal with that? They want you to keep the old one as well. And these are not light on the cost that they incur. These are few TBs lying around somewhere, but you can't just keep around 10 different versions of that. So this is sort of a pain point, to be frank. And sometimes we just have to, we still haven't figured out the best way. But sometimes we'll just have to say, either update your model or this is going to die, or just transfer it to somewhere you feel safe about it. Stuff like that. Yeah. Is there anything? Yes, please.
Different embedding models for the same entity, or is it?
Yeah. So usually when we do that, for example, let's say for follow graph, we tried the skipgram as well as the factorization of that. And again, what's the final way of evaluating them is these benchmarks and the end models that they get used in. Yeah. So that's why this plug and play ability with algorithms really helps. That once you have collected your data set, now you're not bound to one. You can, and again, with ML workflow sitting on top, you can just say, do this with three different algorithms, and I'll come out 3 days later and figure out which one's better. Yes, please.
Sorry if I covered this. I kind of missed the beginning of the talk, but these are word level embeddings. How are you creating a document level embedding for it? Like, you guys try different things you're using the whole document and what works, what didn't work?
Yeah. So this was not specific to just the word level embedding, etc. This is more like, given any entity, can you do X? Specifically for learning document level embeddings, etc. We haven't done much there, but what we are trying to at least do is learn the whole tweet level embedding, and that might also mean, depending on your definition of the document, that can be a document. And then it's not only about, when you think of tweets, it's not just about text. More so, what's really informative is the people who have interacted with it. kind of lends more voice to the tweets representation than only the text. So it gets really interesting, and it's like more than just the document side of things. Yes, please. Uh-huh. Yeah, so as I said, users, words, hashtags going forward, images, anything that can exist within the Twitter ecosystem as an entity or a noun that people are interested in, they should be able to do this for that. This depends on the underlying data distribution shifts. For example, a user's follow graph is relatively static in terms, wouldn't change day over day, especially when you think of our most of the heavy users. So depends on the problem, the underlying data set. There's no kind of golden rule there. Yeah, 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 yeah. Yes, please. Yeah, exactly. So a couple decision points. One is what is the underlying data set that was used to generate this embedding? So let's say one was follow graph, another one was based on the URLs that you post. So the end product user has that business insight as to what is relevant to his particular model, right? Also, something might be embeddings trained on user based on the tweets that they engage with. So you just find a way of exposing the right information and making it available for whoever the decision maker is. Then he's able to pick and choose if he's very thoughtful about it, or because we have many machines and cycles, he can just put everything in and see what happens. Yeah. So the easiest way there is just concat these, all of them, dump them into your model. What we have been trying to do is, can we learn a single universal one but their coverage issues come in at that point. Some embedding has coverage for this portion of the world, another one has coverage for this portion of the world. How do you best do that, etc. So till now we haven't invested a lot in like creating one universal one, but it is a possibility and something we can consider in the future. That's it. Thank you, everyone. Thank you.